Well, right now we have Francois Morain, who will speak about factoring with Oracle.
Okay, thank you for everybody to force me to come here 3 years later. No, it is just kidding because I have some heavy teaching starting in April each year, and so I could not have made it maybe. I'm happy to be there, and thank you for the organizers for trying to improve my level in algebra, which is kind of a desperate cause anyway. So yeah, I'm very happy to be here with mathematicians and so on and so on. So can I start saying things about Hendrik if Hendrik is not here? That's a bit awkward.
What you want to say?
Okay. Interesting. So I'll be talking about factoring with oracles, without oracles, oracle without factoring. And in fact, giving you some historical facts, because we have history, and I think not so many people learn history of a field, and that's a pity. It's even worse in CS. I'm more accustomed to students in CS than in math, but I think it's not a good idea to forget the past. So,
You were saying.
now we can start. So many people ask me, when did you meet Hendrik? So that's the easy part. So you see, it should have been March 26, 1990, I guess. So this was this mythical meeting in MSRI. They seem to have, how many are we who were there?
Yeah, I was there.
Yeah. Okay, not so bad. It was quite important for me because I was young and knew nothing about nothing, of course. Met great people, famous people. And because it was really this title here that stayed until now, Factoring the Dark Ages, which was a talk by Hendrik. The term made its way to Cohen's Bible. And there was also even some video recording of you giving your talk. If you remember. Were videoed or were filmed. And so I could not find the video. Anyway, if somebody, so I think it was, this filming was done by MSRI. So nowadays not MSRI anymore, but some people who paid for their names. Please, I do not. I'm okay with that. But so still, I could not find. Oops, sorry, I could not find the video. It was a time of, let's say, controversy. This was just before the famous attack. I mean, factoring of F9. There was a team and another team. And kind of competition. Okay, I will not cite names because it's so time ago, but I still have a vivid memory of all this period. At that time, QS had outperformed the CFRAC, which caused some interesting remarks by people from the Dark Ages during and so on. And NFS was ready to start, let's say. So if you don't know the difference, then SNFS was the old name for factoring strange numbers, like Fermat numbers. And GNFS, as it was called at that time, was supposed to tackle all numbers. So again, a very important period or conference, at least for me. So what I will be talking about is factoring, and in fact some historical life, say, of some of Hendrik's algorithms. I will tell you some funny things about recent stuff. So you see, I had to write this slide because I had to try to explain some physicists what a number theory is and is not. Okay, so I had to go back to the beginning. Okay, and that for us, factoring means dealing with huge numbers. I will tell you more about physicists. Okay, so what about factoring methods? So this is a list, which is not complete, but anyway. So dark edges means something like trial division, a row, and a bit of p-1. But this p-1 led to a long list of variants. In fact, p-1, there is a p-1 factoring algorithm. Each time you have some interesting group and reduction between the group over Z over NZ and over Z over PC. And of course, the major algorithm of this type is ECM, which was invented by Hendrik, which is a very fast method whose complexity depends on the factor you are looking for and not on N, apart from arithmetic. And it can be generalized to many other groups, as opposed to what we could call metric family, which contains the CFRAC and PQS, NFS, and so on, where the basic task is solving this equation. And once again, one can solve this, can extract square roots mod n, and with some probability you factor n. So there are many interesting things, algebraic things, in this marvelous LNM. So it's reading. Take it and read it, and it's much more interesting than read. So everything you should know about an ordinary extension field is in there. In an extension field or a defining polynomial, it is not just cyclotomic fields, quadratic fields. Okay, real stuff are hard to manipulate, and a lot of gory details about dealing with ideas and so on is in there from a computational point of view. So this is a classical world, Newtonian world for us. And nowadays, when I talk about factoring, I must cite and say something about quantum algorithms. So, okay, it's supposed to work. This is theory. There are crazy papers by crazy authors. The most recent one is this guy here. So, quantum integer factoring, this is the easy part. And S means some small consumption or small whatever, physics stuff. I will say more about this. So what about the life of ECM? So I already told you it was born in 1985, and factors flooded in. Okay, at that time there was only one interesting factoring project, which is a Cunningham project. Okay, so there were all these small numbers expecting ECM to arrive, and then many of these were factored in the first 2 years, something like this. And ECM, still alive, continues to factor big numbers, find large integers. And you see one of the last updates of the Cunningham project, in all there were 31 numbers factored, out of which 8 by ECM, which found large factors like 64 digits, 59, and so on and so on. Don't ask me about the number of curves that was used. I think it's a lot. gigantic bounds, some of which you can find in the ECMNet project. So after the first announcement, there were a very extensive study by the Chudnovsky brothers. And after that, we started a long list of works on finding, let's say, good curves. At some point, you say you look for curves for which a reduction mod P will have a large torsion group. And generally, you take your favorite curve over Q having a large torsion group, you reduce it mod P, and then you hope that the reduction will be better than a standard curve over FP. So in fact, Peter Montgomery started this, and it was continued by Barbulescu and co-authors, trying to find a good definition of what an elliptic curve is good for, or what is a good curve, maybe. So Barbulescu was able to relate this with Galoisian properties of torsion points, as described by Serre, and you can find much more in his papers. And I slightly tried to extend it in a recent paper for Hans. What next? There's a reference implementation, which is called GMP ECM, that everybody uses. And this is the core of ECMNet, which is something that you download and then you start trying to factor numbers in a semi-automatic way. So just for fun, this is a chart of the largest factor found on the Cunningham number through the edges. So, yeah, I'm not sure this is really interesting. You're looking at something that should be a log P curve, because it doesn't happen every day. But you find a large factor. You see the record is somewhere here at 83 digits. And you see that it dates back something like 10 years ago. So it's not going very fast. Just to indicate something about this year. At least it works, still interests people. So that's very important. And that's considered to be the best method to find small factors like, I don't know, 40 to 50 digits. And after that, you have to work hard. Okay, what's the situation of classical factoring? So, this is a complete history from 1970 up to whatever, 2020. Here you see a lot of things, okay? So this was pre-crypto, okay? Asymmetric crypto. And after that, hop, there was this takeover of QS over CFRAC around 1984, something like this. And until the two NFS variants appeared somewhere around just before 1990. And you see you have slopes like this, and you have the green curve, which is for special numbers like Fermat numbers, powers, etc., etc. And the red one, which is supposed to attack any number, and in particular, RSA type number for this asymmetric crypto system. And as you can see, it is hard. Okay, you see, for instance, F9 was factored around 1990, let's say autumn, or cannot remember. And you see the first 150 decimal digit RSA key was factored 10 years later. So this tells you something on the difference between having a good representing polynomial and some ugly and even optimized polynomial representing the number you're trying to factor, which is one of the key ingredients of NFS. And you see that there's still this difference, special number field sieve here, okay, with almost 360 decimal digits, and this RSA key. Okay, so now we have 110 decimal digits difference. So again, this tells you something. This tells you also that pioneers in factoring are retiring, and that less and less people factor big numbers, which might be a problem in the short term. Okay, what next? Yeah, you can see plenty of things on my thing, but I mean, I don't spend all my. So just to show you again big numbers, you see this is a defining, this is a number you want to factor. In this variant, they use two polynomials, one which is, sorry, this one has some very interesting properties like what we call projective roots and things like this, meaning that people try harder to find a good polynomial with many roots, not small p's, because you see this guy is really smooth. And each time you reduce it mod small primes, you get interesting norms. Okay, and now it's a job to build this type of polynomials adapted to a number. Again, many algebraic details are concealed here. And you see that it's very rare in textbooks where people explain you how ideals behave here, how they can be computed, and what are their properties, okay? Particular factoring properties. Everything in this is in the lecture notes I already mentioned. So quantum factoring. So that's a boring topic because there are many more physicists than mathematicians, and they try to convince you that they are the best every time. It's very difficult to work with them because they don't know what a theorem is. So you see, they came to me and we discussed with Ben Smith and so on. And so each time they conjectured something really stupid, I told them this cannot be. Here's a theorem explaining why you're wrong. They won't listen to me, which is really sad when you believe in science or something. So what happens? So except maybe for Sheldon, who was already mentioned, no one can build a quantum computer in his garage. I don't know if you tried. Interesting example. You need to cool a real fridge. I mean, I don't know if you know, but quantum computations must be done around zero, the absolute zero. Otherwise, the photons strike you. So it's not doable. So also, I think I won't see any quantum computer working because nobody cares. Because we don't know what to do with a quantum computer, except factoring integers. But are you sure that if you manage to factor an interesting number with a quantum computer, you will be free to say it? So the only people who cares are agencies with 3 letters. It's a little more letters in France, but I mean, it is the same. So I guess you cannot make money out of this. And in fact, there are also very difficult physical problems to solve, to make it work. And also because you see the number of gates you need to factor an n bit grows as big O of n to the third. meaning that if you are targeting a 1,000 bit number, you need 1 billion gates. You are very far from it, actually. I think the most damaging thing in its history is that now young students, they want to look at post-quantum things, sometimes quantum things. Okay, I mean CS students. And who cares about post-quantum things since we don't have quantum things? And so everybody wants to do something that is science fiction at a certain point, and forgetting about mathematics and things like this. So we might well end the story with nobody being able to factor a number, but still waiting for a quantum computer. I'll be retired soon. But I mean, situation can be critical. I don't know, depends on states and whatever, but something sad is happening. Anyway, so oracles. So we are back, almost back to what we understand. So in complexity theory, if a problem is difficult, you say, okay, up to which point can I add extra information until the problem becomes easy. And so this is typically the case of integer factoring. So what is the core of Shor's algorithm from a numerical point of view or from a number theoretic point of view? This is an order oracle. Okay, you input x and n, and you want the order of x modulo n. And if you have luck, this order will be enough to factor n. So the favorite example is 15. Okay, 2 has order 4 modulo 15, and you can manage to factor 15 out of this. So if you look into this very somewhat more deeply, you realize that 15 is one of the rare numbers for which all elements have even order. Okay. That's a difficult question, and then you can generalize and see what happens. So it means that basically when you have your physical apparatus, whatever it is, you input 2 and 15, and you are sure to get the order 4, and you can factor 15. And many physical experiments use special numbers for which maybe one application of the big box will be enough to factor. I may call that cheating. And the problem that our distinguished physicist asked us about was, is it possible that the oracle order will always give an answer that enables to factor n? I told them this is not possible. That's easy. Look at this number, you cannot factor it, and blah, blah, blah. And I can build an infinite number of numbers that you cannot factor in one step. It's not very difficult to build, and they won't believe me. So they insisted that their conjecture should be true. I told them, I insist that the conjecture is false. And then we stopped talking because it was no use. Sad, but true. Okay, so looking at more interesting things, there are RSA oracles and there are number theoretical oracles related to factor. Okay, so of course I have to speak about LLM. Nobody did, I guess. You're supposed, all of you are supposed to know about LLM. Yes. Anyway. So this incredible theorem tells you that given a lattice, most probably with full rank, generally with full rank. We can find a short basis, short being described by this inequalities here. And what is the most striking thing maybe is that it can be done in this deterministic polynomial time in the dimension and the height of the coefficients of M. And so how is it used? Generally, in many applications, you find some guy, some vector whose norm is below this quantity. And this means that it should be a linear combination of the PIs. Okay, and really this is what is used in practice. So what's the life of LLL? Again, algorithm, and then you wait for applications, implementations, and starting a new life, real life. So I was there, and so I lived that part. So in the beginning, people had trouble programming LLL because you seem to use a rational arithmetic, and the computers at that time were slow, and you could not do a large dimension lattices. And in fact, and also so many people worked on floating point version because it should have been easier to use. So there were private implementations in the world, and for me, the first available implementation was in Paris GP, around 1990. Okay. Same question mark? Zero? Okay, so 1990. And with the famous functions, the lindep and altstep, that many people admired. And at the same time, people in crypto realized that it was an incredible tool to break crypto systems. And basically, crypto systems based on lattices, like knapsacks, all variants of knapsacks, new systems, and so on and so on. And many people specialized in the use of LLL in cryptanalysis. So this is not all the story, because there are nowadays a lot of proposals reviving lattices, polynomial rings, and things like this. And so new developments of LLL on algebraic number fields in orders, things like this. It's very interesting and of course full of algebra and algorithmic and practical implementations and improvements with strategies to speed up reduction, like block corking the tariff and things like this. Is it available? Yes, there's a famous program called FPLLL. Remember, it still is H at this point. Anyway, so this is a floating point LLL that is available. Now it's embedded in Python FPLLL with a more, let's say, a nice interface. And you can find LLL in any major mathematical system. And the only thing to understand is that there are two types of mathematicians. The one for which the action of a matrix is row major, and the one column major. Yeah. You can survive this, that's okay. My nightmare. So I can tell that Magma is a row major mode, and GP is a column vector mode. Okay, so LLL has a good life. Still is still very important. Even in chemistry, but it's too yeah, I won't tell this one. So one of the most important theorem in oops. Very far away. What am I doing? I'm still going, okay. This one. Okay, so one of the most, let's say, cryptanalytic theorem standing or using LLL is that theorem of Coppersmith, who is able to find small roots of polynomials, model, a composite number in polynomial time in these parameters here. Okay, so just to give you a flavor of how this type of thing works, you have your polynomial here, and you build this matrix. Okay, this is not optimal, but it gives you the idea. So when people build lattices, in fact, they don't want to compute complicated determinants. So generally, it's upper triangular or lower triangular, so that you can compute the determinant here just by inspection. So this is one of the key things. After that, you try to solve this equation. Px of x0 is 0 times n for some x0 and y0. You build this vector here, and you want that the image r times n is small. You do some scaling here, and you remark that the norm of S is small. And the rough idea is that if you find S such that S to the power delta plus 2 is below this formula for the determinant, again, this means that S belongs to the reduced basis of LLL. Okay, and you replace this by, okay, I will try to replace S by square root of delta plus 1. If the result is true for this, it's true for this, and so on. And then what happens is that you find a bound on your X here. So basically, if X satisfies this equation, there is a solution x0 of our problem with X below big X. So you see that dependence here is not so good. If you enlarge your lattice, then you can go up to X equal 1 over delta. And this is enough to break crypto systems, RSA records, as I will show you later. There's also another version of Coppersmith, sorry, that is able to find a rational solution to bivariate polynomial here with x0 and y0 relatively small, provided that this condition here is satisfied. Okay, you have kind of norm here, W max of P tilde here after scaling, and if this condition is satisfied, and that's it. I will give you an example of this later. And so this type of theorems can be extended to many cases. Every time the recipe is the same, build the lattice for which you can compute the determinant and see what happens. Sometimes results are kind of asymptotical at infinity, because there are hidden constants here. Anyway. Okay, application. One of my favorite papers of Hendrik concerning divisors in residue classes. A long time ago, there was only one primality proving algorithm called Jacobi-Sums test, which succeeded to the Gaussian test and so on and so on. And there is an algorithmic problem to be solved at the end. We have to find divisors of an integer n, given that there exists some s, which is of size, in generality, it was something like n to the third. Given that all divisors should be congruent to R mod S, because it was a consequence of the other part of the algorithm. And so Hendrik proved that in fact we are at most 11 numbers, integers solution to this problem if n is greater than 1. Sorry, if alpha is greater than 1/3. And in fact, there is a function alpha, which tends to explode at 1/4, giving the answer. And there is a table of this. You see C alpha is 2 for alpha very large, and some other values here. And what is also very important is that these 11 divisors can be found by a very nice Euclidean algorithm type, Euclidean type algorithm that can be used for that. So many problems like Henry showed that C of 1/3 is greater than 5. So we don't know many more things, despite results by Broders and Akers through these years. There are many more points. I must say, what is it? Lower bounds for C of alpha. So things are still open, and that's fine. And so we arrive at something which is really important to know, is this axiom. Everything you can do with an Euclidean-like algorithm, you can extend it with LLM. Okay, so now it's a well-accepted axiom. So I should say that some people believe that the inverse axiom is also true, in the form that I don't understand anything about continued fractions, but I replace it with LLM. I have names. So what Coppersmith, Howgrave-Graham, and Nagaraj did was to propose an LLL variant of the algorithm to find divisors in residue classes. And so you see the typical result here. You have to bound everything as a power of n. So many alpha, betas, and so on. And you end up with some inequality. So giving valid parameters for the approximation of whatever. And so a domain in which you can solve all the problems with LLL. And of course, LLL means deterministic polynomial. Okay, so details are not very important. It's just principle that is again applied, build the lattice, compute the determinant, and then do something to other. So LLL, and they also improved the value of C of alpha, but this has nothing to do with LLL. And what is interesting is in practice, if you try to do statistics, 1/4 doesn't appear as something really special. But this is the way things are presented here that makes this function mysterious. Anyway, RSA oracle. So why is an RSA oracle? Basically, it's a bug introduced by a programmer. Okay. When you tell somebody to implement RSA, that's hard. Talking about the theory, that's even harder. So you want to speed up things. Okay, and particularly if you are programming RSA verification on a smart card, you want to make this fast. Otherwise, you lose your clients. This is how you can translate it. Okay, and so people try to invent things, and the first oracle, say, is suppose that I know half the bits of prime in RSA. Maybe the most significant bits. Can I factor P? N. Answer is yes. using some variant of a Coppersmith algorithm. So more, so this is not really, I mean, yeah. You see, you can implement a RSA key generation. You have a stupid random number generator. And you see, yeah, it takes time to, I don't know, generate 256 bits random, or 512. So maybe I can have the first 256 fixed. And after that, I just add some random stuff. So that's a security issue, but I mean, that's life. You find it, etc. So there was a famous Wiener attack. So this time you say, oh, okay, to decipher, decrypt, I need to perform some operation like x to the d mod n. So I will use a Chinese remandering theorem. So I have to do that. First idea is to have d small. So why not use a d as 1.28 bits? And that's enough. Problem is that if you do that, if d is too small, then there is a continued fraction algorithm used by Wiener to recover factoring. And applying that axiom, of course, you can improve this in LLL, giving more elaborate bounds, larger bounds. Second thing, I want to decipher mod P and mod Q, and then recover the answer by a Chinese remandering theorem. So why not insist to have my decryption key D, small mod P minus 1? The problem is that you can solve and factor n in polynomial time, if you think about it. So I already said something about MSB and LSB, many variants. And there are crazy implementations. Like, I don't know why people think about this. You have to generate two keys, P1, Q1, P2, Q2. And you know that P1 and P2 share T bits. Crazy. And you can break it. And there are a lot of stupid proposals. So people might learn a bit of number theory. Better for them. So what about now number theoretical oracles? So first of all, this cute algorithm. Suppose you know how to compute the nth term of tau of n, which is a coefficient of development, expansion of delta of q. Then you can factor n equal pq in deterministic polynomial time when tau of n is non-zero. So I remind you, if you find n such that tau of n is equal to 0, then you are famous. Anyway, and it probably never happens. Who knows? So how does it work? Okay, you know how to compute tau of n squared, and you know how to compute tau of p and tau of q. There is this magical identity here, as a sign equal too much. You develop, and then you see that you know the sum of these two terms, and the product is just this formula. Okay, so addition and product of two numbers. So you get two numbers. After that, you have to treat some cases like if P divides tau of Q and so on and so on. But then you can factor n. Of course, there were progress in computing this, but I'm not sure it works for opposite numbers. So now what interests us much? So okay, everybody knows this. Okay, phi of n counts the number of invertible, blah blah blah. Euler, Fermat, and the two famous, long-standing conjectures. We cannot compute phi of n without factoring n, which is more or less the basis of the security of RSA up to a certain point. And this other conjecture, if I know phi of n, I can factor n. And so I will concentrate on the second problem. So, of course, if we accept random polynomial time algorithms, then that's not difficult given phi of n to factor n, because basically phi of n, I'm assuming n is odd, phi of n is even. So you can find many solutions to a square congruent to 1 then, and one of which will give us factor we're looking for. But with probability 1/2, you repeat stuff, and you're done. More than that, if ERH is true, then this can be made polynomial time deterministic because there will be a good character inside a small part of the over n star, and that's done. What happens if you look at this problem without ERH? In fact, this approach will be enough to factor n. Because I mean, the least integer m such that z over n z star is generated by integers less than m is given by this formula. So this is deterministic polynomial. Okay. Complexity is even worse than the first version of AKS. Okay. But still it can be done. Okay. But now the thing is, suppose we are quite demanding in the sense that we want to find deterministic and unconditional results. So the typical result that we teach to our post students is that when n is really RSA number, then phi of n, if you got it, then gives you p plus q, and you have pq because that's product n. You solve the degree 2 equation, and that's done. And the question is, can we do this for more general n? The thing is that there are some results known on that. For instance, Landau's algorithm reduces the problem to square free n. We will give you some hint of why this is true. And after that, you can consider two oracles. First one is something that gives you phi of n, and the second, factorization of phi of n. Okay. And so the second oracle should be more powerful than the first one. Okay, so Landau's algorithm, basically, you start as a first step by computing a GCD of n and phi of n, and you see that if n is not square free, there's a packet here of primes that will appear, and recurring in the good way will give us a lot of information, and a writing of n as a product of vi to the power I with vi prime to vj. And now we just have to consider square free n. Okay, and the number of these guys here, is bounded by okay. Okay, what is the phi bar oracle, which is supposed to be the most powerful one? I have the factorization of phi of n. So in theory, I can compute all divisors of phi of n. And my primes I'm looking for are 2 delta plus 1, where 2 delta divides phi of n. Okay, so that's a naive idea. Does it work? Times. Can it work always? The answer is no. So it's a pity that Carl is not here. Anyway, we made some publicity for him. First of all, you remember that the number of divisors of some m, which is a product of pi to the alpha I, fi, is on average log n. But there are numbers which have an exponential number of devices. Then you're dead. Up to some. And this is even more so that there is this shocking theorem by Luca and Pomerantz, which means that really phi of n has a lot of devices. And I would say a lot more than a standard number. It's also not hard to imagine because you see phi of n is a product of pi minus 1. So pi minus 1, there's already a 2, or power of 2 that goes in it, and then you can find much more. So definitely this naive approach cannot work for all numbers. Okay, so you have to work more. So this problem is resisting up to certain. There is an approach by Stralek close to primality approaches by fellow Koblitz and Pomerantz. The setting is a little more general, but you can imagine that M is phi of n. And you just have to suppose that p minus 1 divides m for all p dividing n. Of course, the case for m equal to phi of n. And the algorithm says, okay, I can select a certain number of integers up to log n squared. And I try for each of them, we compute b to the m minus 1 mod n. It happened that it has non-trivial GCD with n. We are happy and we stop. Otherwise, we may compute the order of b mod n since we know the factorization of m. Okay. And then after that, since we know the order and its factorization, then I can try to compute all these GCDs. And I will stop as soon as a non-trivial factor of n appears. Okay. And if this doesn't work for any b's, and you are left with the property that for all your numbers in B, the order of B then is equal to the number, to the order of B modulo pi. Yes. After that, you have to use this result here to try to finish factorization of n. And the claim of Stralek is that the algorithm will work in a sub-exponential deterministic time. So the sub-exponential is not related to NFS, otherwise it would be just too easy. Okay, it's a little better than NFS, and it's deterministic. Let's say I'm not completely sure my understanding of this. Okay, so this is supposed to be the best result when the factorization of phi of n is known. And you see that's not completely satisfactory. There should be resisting elements. And now the funny part, how do you find difficult numbers for this guy? You cannot, since ERH is true. Okay, it's impossible. Otherwise, I disprove ERH and I become famous and blah, blah, blah. But I mean, there's no chance to find a difficult number. That's strange. Okay, so last part, what we did with colleagues. I mean, if you, once I have explained all this about LLL and Coppersmith and so on, that's not very difficult to realize that what we have to solve for finding a p dividing m is that p divides n, p minus 1 divides m, and we can make it enter a Coppersmith scheme to solve the problem. So, as usual, I suppose that m is n to some power, p, the factor I'm looking for, is n to the power alpha, And I claim that we can recover P in deterministic polynomial time, provided 1 plus theta is less than 4 alpha, which readily means as a consequence that if alpha is greater than 1/2, this condition is always satisfied, and then I can factor any number with its largest prime factor greater than square root of n. So basically, how does it work? You rewrite your polynomial, your conditions here. This is you're looking for n is x0 times p, m is y0 times p minus 1, and this means that x0 and y0 are roots of this polynomial in 2 variables. You know that you x0 and y0 have given are bounded by these 2 quantities, okay? And these, in fact, are small, one point. And then this is a use case of Coppersmith bivariate theorem, and we use LLL, and we win. What are called compact numbers are numbers for which all the prime factors are below square root of n. And so it seems that, I mean, these numbers I cannot deal with. So maybe it's one reason why these numbers are numbers with closed, with prime factors of closed size are maybe more difficult to factor than others. But this is just one way. So what can we do? We can optimize this, and in fact use algorithms by Howgrave-Graham with continued fractions or LLL, and we can attack numbers for which one of the exponents and the size of some prime factor satisfies these conditions. And this can be done in deterministic polynomial time, since we have LLL. Okay, let me summarize what happens for k equal 3, which is first example. I claim that with all the preceding results, we can find factorization of m given phi of n if one of these conditions here are satisfied. And this leads to this incredible picture. I can factor n if I am in any of these regions here, except in the gray one here. And see there's a little triangle here in which I can do something. And similar things for, I guess, a larger number of divisors, but I don't know how to write things in dimension 3. And so that's a cute picture, maybe. Anyway, so that's about all. I told you we tried to find some results on the phi oracle. I think the first time the size of the prime numbers are important. Why not? And we prove similar results for lambda of n, sigma of n, of course, and the order modulo n. We have partial results. And this is all I have to say. So again, thank you for this great algorithms. And that's it.